Alright. So last time we were looking at actually creating a magnetic field. And we learned that a moving charge creates a magnetic field. Simplest case, all the charges are moving in a straight line. So we have some current, several charges moving across an infinitely long wire. Point our thumb, wrap our fingers around, we'd see that the magnetic field would be going like this at some radius r, and the magnetic field strength would be equal to permeability of space times the current divided by 2 pi r. We did a simple example for the bell ring. We have two wires. One is having a current I1. The other is having a current I2. They are separated by a distance of r. And because of Newton's third law, equal and opposite reactions, every action has an equal and opposite action. We know we can just analyze the force of one, and the other force has to be equivalent. So there are going to be some charges going up and through here, but this one's going to create a magnetic field. So again, it's going to loop like this. So the distance of the circle, which I'm drawing horrible circles. So let's go create a magnetic field. We know the magnetic field, I'll call this B1, is equal to this equation. And we know that a moving charge, let me actually pull up so I don't make any mistakes. So because this magnetic field is going to be pointed into the paper, B is pointed into paper, the charges are moving in this direction. So putting my thumb in the direction the charges are moving, my fingers in the direction of the field, my palm would point to the left. So my force is going to be toward the left, assuming that the current is going up and up in both of them. Again, I said that assume currents are positive charges. In actuality, we know that the current is electrons moving, but back whenever Benjamin and Franklin was working on electricity, they haven't really discovered the electron and other things, and didn't know about atoms. And he just guessed whether or not they're positive or negative. He liked positive over negative, so he guessed their positive charges number. Makes no difference. Remember, in physics, all a direction is a positive or negative sign. So having a positive charge move to the right is the exact same as having a negative charge moving to the left. Or no, it's the same thing as flipping the sign of a negative charge and moving it to the Well, yes, the same thing as this. Because if you multiply so this is a negative charge. If I multiply this by -1 to make it positive, it also changes direction. So by multiplying this negative charge by -1, the value becomes positive and the direction flips. So it's equivalent. So we know that a moving charge in a magnetic field also experiences a force by Lorenz's law. So force is equal to Q times the velocity cross product with this. And they're at 90-degree angles in this example because these two lines are parallel. So because they're at 90 degrees, we can ignore the fact that this is a cross product. The theta is going to be 90 degrees. And the sine of theta, sine of 90 degrees is 1. So what would be the velocity of the electrons, or positive charges, I should say, moving in a wire? So let me reintroduce current. So current is defined as charges per second. So current I is going to be equal to Q per T. Our amperes is equal to coulombs per second. So how can, so velocity is going to be distance over time. So what's a distance? Let's choose some arbitrary distance. Let's choose some arbitrary length. I'll call it some delta L. Or I'll just do it like this. So some arbitrary delta L, some length of the wire. So I know velocity is equal to distance over time. So I got a distance. Current has a time unit in it. So if I multiply current times a distance, what values do I get? So current is charge over time, and delta L is going to be some distance. So rearranging this is equivalent to, well, this is velocity, right? Distance over time. So that's equivalent to charge times velocity, or this value right here. So taking your current and multiplying it by some length of the wire, I get a velocity. Thus, because I know this is equivalent to charge times velocity, I can plug it into the equation. The current, and this will be current 2, times the delta length, the length of the wire, times the magnetic field B1 is equal to this, I'll call it F2, the force on the wire. And because I know B1 is this, I can plug that in. I get that the force, and the force is going to be equal on both wires. It's equal to magnetic permeability of space times current 1, current 2. Divided by 2 pi r times delta length, the length of the wire. And usually we will express the force as per unit length, like this. So let's do an example problem with this. Suppose you have two wires. Two wires of length 2 meters. Technically, this does not work for this problem because we assume the wires are infinitely long, but it'll come up with an approximation. It's close enough. 2 meters is well over the limit because the charges are so small. You send 5 amps of current through one wire. Or better yet, let's just draw it. So I got a wire like this. It goes through your TV, does some weird stuff, and then it comes back down. So if I send through this 5 amps of current, it's going to go through the circle, and 5 amps of current has to leave out, right? And let's suppose that these are right next to each other. Let's make it 2 millimeters. So they're separated by 2 millimeters. And we have a length right here equal to 2 meters. Is this going to, are the two wires want to come together or push each other apart? So in our classical example, we assume they're going in the same direction, and it was attractive. Another way of doing this is to go through your thing. Current going up here. Your wrap your fingers around this wire. You would see that the magnetic field is going this way. The charges are moving downward. So put down, and the field is going into the paper, so your palm pushes to the right. And by Newton's law, we're going to have an equal and opposite charge force here, pushing it away. So the question is, how strong is that force on the wire? So I know my I1 is 5 amps. And I'm going to use, by the way, magnitude is either done using 2 lines, but sometimes it's just approximated with absolute value lines. I2 is 5 amps. Note I'm getting rid of direction because I know the direction already. My distance, R, is going to be 0.02 meters. That doesn't seem right. 0.002 meters. And my length of wire that I'm working with is 2 meters. So the force is going to be mu naught I1 I2 divided by 2 pi r times my length I'm looking at. So what is the permeability of free space? It is 1.25664 times 10 to the negative 6 meters, kilograms per second squared, amp squared. Then we have 5 amps times 5 amps. That gets rid of the amp squared. Then 2 pi times 0.002 meters. That gets rid of the meters. And then I'm going to multiply this whole thing by 2 meters. Which leaves me with kilograms times meters divided by second squared, which is newtons. Which gives me a force of 0.005, almost exactly, newtons. A very, very small force, which is what we expect. We don't see wires flying off of each other whenever we turn the TV on. It's a very weak force. How can we make this force stronger and make more powerful magnets? Yes. That's how many amps do you think until these wires fall apart? So it's with the square. You're right. So during a wire, so I'm sending a current through it this direction. So we have around it all these magnetic fields. But they don't overlap. They don't. Well, magnetic fields don't overlap anyway. But they're. Again, let's look at the flux. The flux is. I drawed all these lines. So the centers of them on the wire are all equally spaced. That's how you do lines. Remember when we did it on this? I equally space them out from my center point or whatever. And then this really get intuition for how strong it is, draw a loop of area, count the lines through it. If you want to see how strong it is far away, count the lines using the same area. So we see that they're all equally spaced out. Now then, I'm going to take this wire and I'm going to bend it into this shape here. How does that change the magnetic field? I just made a circle. Well, let's again, I'm putting current here. Current will come out here. So let's draw some evenly spaced dots along this wire. And then draw the magnetic field at each of these dots. So current is coming up here. When I wrap, it's going to wrap like this. Again, same thing here. Same thing here. I really should have used a bigger radius to illustrate it. But I'm hoping you see, let me actually do that. Let me just redo this. To really illustrate this. So I have current coming up, current coming down. I'm going to draw some evenly spaced dots and then draw a magnet field, each with a radius. What do you notice about the magnetic fields closer to the center of this loop? Which means the magnetic field is stronger there, right? So, by orienting it into a loop shape, outside this loop, it actually got weaker. So here it's about uniform all the way out. It's uniform at every distance. But here I'm concentrating the magnetic field lines toward the center. They're getting stronger. Some of them are overlapping. But outside it's getting weaker. That this is what it actually looks like. So they're all going. So magnetic field lines are going to be the sum of everything. So I really can't draw these closed loops like this, as they're going to overlap and combine together. The overall shape is going to be circles like this. Toward the center is almost entirely like infinite radius circles. They're going to basically make a circle that wraps around the universe at the very center, and they make around here circles closer to this. So once you get closer to this, right here, they're more circular around the wire, but toward the center, they all combine and make very powerful loops. And this value right here is the magnetic field strength at the very center. That's important. It is not, this R is the radius. This radius of the circle R right here. The value of this field is only for the single point in the middle. Note, for this example, this field strength tells you the exact field strength for any point. That's a distance of R away. But you have to know how to solve calculus. And basically, they chose an easy calculus formula to solve for at this point right here. And thus, we get only this one formula. It's too complicated to solve for it. But let's now do this example. So let's compare a single wire that has a current of 5 amps, and let's get a distance of 2 centimeters away, versus where we take a loop where we put in 5 amps, 5 amps come out, and a distance, the same distance right here, 2 centimeters from the wire in the middle. So this one will have an equation equal to mu naught times I divided by 2 pi r. And we get a value here of 5 times 10 to the negative 5 Tesla. And this equation is almost the exact same. The only difference is we're missing the pi, so it's a factor of pi larger. We get 1.5708 times 10 to the negative 4 Tesla. So it's exactly 3.14159 pi. It's exactly pi times as strong. Can we do better? How? Can we make a stronger magnetic field using 5 amps? Yeah, that would work, but there's something better you can do. We're going to actually learn the most common way of actually doing it, and if you want to make an electromagnet for yourself. So we know if we put a loop, we're going to get stronger, as all these lines are going to converge. In fact, we see that when we create a loop, they bend so it's going outward like this. What if I put a second loop there and put it next to each other? Well, all the magnetic fields are going to go through the first loop and then the second loop, and they're going to be stronger. What if I put another and another? You're going to get this shape. It's known as a solenoid. So, current is coming up here. And, so current is going through here. So if I wrap my fingers, put my thumb in the direction of the current, and wrap my fingers around the wire, my fingers are going to have to go grab it inside, right? And if I do it the opposite here, if I put my thumb going down, I want to go through these wires, but when you see the wires are close enough that they shield, you would have to, it's weird, I can't hold it like that. But you can assume that no magnetic field is going to try to leak in between the wires. So all the current is going to go through all of these. And we get this shape right here. It's called a solenoid. So we have some loops, and it's a horrible looking solenoid. Let me make it. So the magnetic field lines are always going to be pointed through it. And in the middle of the solenoid, it's basically linear, by the way, or uniform throughout it. So at any point really in the middle of it, because if you look again, the density, if you look again at the density by drawing a circle and looking at how many lines go through it, you'll notice it's basically the same throughout it. So at any point inside the circle, it's equal to, the magnetic field is equal to mu the permeability of whatever space is inside of it, times N times L. N is the number of loops, number of turns. L is going to be this length right here. And this is going to be your permeability. If it's a vacuum or air, then it would be mu naught. That's the permeability of free space. But we might not have free space in there. Or empty space. And I'm wrong. That's current. Hold on, let me look this up. I think I got this completely wrong. Yeah, my bad. Wrong formula. It's equal to permeability. It might not be mu naught. And this is an approximation. It's equal to the number of turns divided by the length. So this is number of turns. Length times current. And usually we approximate this as this equation, where this is the turn density. So, for example, how many turns per meter? And this value, we'll see in a little bit. If it's a vacuum, it's equal to mu naught, or if it's air. But we can actually make this stronger by using iron. By you putting an iron core in the middle, we can significantly increase the output. Because iron allows that's the reason why iron is magnetic. Iron enforces the flow of magnetic fields. So, let's do our example. We're going to have a current of 5 amps. We will use a vacuum for right now. Our permeability is equal to permeability free space. So 1.25664 times 10 to the negative 6. And what's a good turns per inch? Or per meter? Let's do how many turns do you think we can get per inch? Then we'll convert from there. I don't really know. Let me get you some so that you can actually compare. Alright, how many turns do you think are in this? This is about an inch. How many turns would you count there? And they're layered on each other. You can put turns on itself. Eh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 30, 40, about 4 liters deep, 40 times 40. Which would be 160. Assuming I'm off by a factor of 2, I would guesstimate that's more like 500 turns is pushing it. Your estimation skills are not good. So, the turn density, 500 turns per 1 inch. I don't like inches. So 1 inch is equal to 2.45 centimeters. 1 centimeter is equal to, 1 meter is equal to 100 centimeters. So inches cancel out, centimeters cancel out, and I'm in turns per meter. So that is a density of 19,685 turns per meter. I'm just going to round that to 20,000 turns per meter. So our equation, B equals this. So 1.2566 for E negative 6. So let me just write that out. Turns is obviously a fictitious unit. And then we have a current of 5 amps. And let me make sure this is right. So a meter and a meter cancel each other out. An amp squared, an amp divided by amp squared. So I get a unit of kilograms per second amp squared. What is a Tesla equivalent to? It's equivalent to a kilogram divided by an amp divided by a second squared, which is what we got. That would give us 0.125664 Teslas. Remember, was Earth's magnetic field strength? So Earth is equal to 0.000032 Tesla. Your fridge magnet fridge magnet is equal to 0.005 Tesla. Strength of the sun. So a sunspot, 0.3 Tesla. Neodymium magnet. This is the very, very, very strong magnets that you can buy. It's like one of the strongest magnets you can buy on the market. At the surface, they're 1.25 Tesla. So, by just winding around a lot, putting 5 amps of current, we get a pretty dang strong magnet. Almost as strong as a sunspot, not quite as strong as a neodymium magnet. Now let's look up the permeability, the magnetic permeability of iron. The magnetic, so iron, Fe, iron, its magnetic permeability and let me make sure I'm getting the right number. Is equal to 5,000 times mu naught. So basically, I multiply our previous number by 5,000 if I use an iron thing. So that means using iron core, the center of it will be at 628.32 Tesla. Which I can tell you is definitely not what we can achieve. This is where it begins breaking down. Why did that not work? Let me make sure. That is the reason why is 628 Tesla is stronger than the surface of a white dwarf. The current world record for continuous magnetic fields is 45 Tesla. So, I don't think I made a mistake. I think the 500 turns per inch is wrong, is too big of an assumption. I think this number here is what's doing it wrong. There's a lot of loops to put in an inch. I think it should be more accurately 100 turns per inch is pushing a limit. But we're going to make next week some electromagnets. If I can find my magnetic wire. Do you know what magnetic wire is? Magnetic wire? Which is a fancy name for some copper wire that has a very, very thin insulator on it. It's copper wire that has some sort of resin on it. What this means is that instead of having a wire and then having really, really big plastic around it, we instead have a wire and the smallest possible insulator between it. Which means when we loop it around, we can get the wire super, super close. Hence the reason why it's called magnetic wire, because it's used in making magnets. We need to pack these wires as tightly as possible. And usually it's just coating it in a very thin resin. So MRI scanner is about 12 Tesla. Superconducting magnets are about 4 Tesla. Oh, no. It's 1.5 to 3 Tesla is the strength of... I need to look up. I forget this. I forget the reason this is. It's either the fact we can't access this number. And the bell rings in 2 minutes. So, do note, however, when you have a solenoid, this is just the strength of the inside of it. And, when we use it, we're going to use it right here, basically. Right over here, if you remember, when they loop like this, we don't have very many lines right here, but we have a lot of lines coming out this end right here. And this is going to be significantly less than the very theoretical core. I need to look up why we're getting such large values for the inside that beat world records. But that'll be for next week.